Hello, I'm Yongpeng He from University of Bath, UK. The topic of my presentation is the discrete topology optimization methods with feature size control and its application to partial double-layer gridshell design. This work is done by myself and my supervisor, Shepherd and Jie Wang. Gridshell structure consists of discrete members, which are usually made of steel or timber. Owing to the capacity of covering large span and providing column-free space, as well as embracing free-form geometry, gridshell has been widely applied in practice, such as the exhibition pavilions, airports, stadiums. However, gridshells are also vulnerable in stiffness and stability. To enhance the mechanical properties of the gridshells, we can add the second-layer grids to the single-layer structures. Here are some examples of gridshells with partial double layers. The challenge is the identification of the configuration path for the second layer grids, especially when free-form geometry is considered, where irregular boundary, drastically varying curvatures might be present. We propose methods for topology optimization of discrete structures with feature size control and apply these methods to identify the place for second layer grid additions. The feature size mentioned here is defined as the radius of the minimum circumscribed circle of the same phase elements. Here is a typical result of the topology optimization of discrete structures. The black lines represent the solid elements which are present. The gray lines represent the void elements which has been removed. The red circle circumscribes the solid elements, and its radius is defined as the feature size of the solid face. The radius of the blue circle is the feature size of the void face. The topology optimization problem is formulated as follows. The design variable is chosen as the pseudo-density of element. The material stiffness is interpolated using the same approach. The objective is to minimize the structural compliance. The constraints include the global and element-wise local material constraints. We perform filtering on element density to achieve minimum feature size. We incorporate the element-wise local material constraint to achieve maximum feature size. Here comes our first example. The design domain of the cantilever beam is shown here. The results obtained without filtering shown in A. With filter radius 1 and 2 are shown in B and C, respectively, in which the solid elements have lumped to display a minimum feature size close to the specified filter radius. Next, we consider simultaneously the minimum and maximum feature size. The originally large components has been split into small parts to satisfy the maximum feature size control. The smaller the R maximum, the more sophisticated the connectivity relationship in the structural layout. Now let's consider another example. The design domain is shown here. The results obtained without filtering is shown in A. The results with different filter radii are shown in B, C, D, demonstrating the lumping effect caused by the filter. The results with both minimum and maximum feature size control are shown here. Similar to the previous example, in general, the feature size of the solid face falls into the specified range. The smaller the R maximum, the more sophisticated the connectivity relationship. Here comes our third example, a hexagonal dome. A uniformly distributed load is considered. The optimal structural layout with both minimum and maximum feature size control are shown here and are used to guide the design of partial double-layer gridshells. The addition of the second layer grids is conducted based on the dual principle. The optimal structural layout, the button cord, the web members, and the partial double layer gridshells are shown here. A brief linear static analysis is conducted. The deformation contour shows that the maximum deformation appears at the midspan area between two closely neighboring supports. Based on our research, we can draw the following conclusions. A method for topology optimization of discrete structure is proposed. It can control the minimum and maximum feature size of the solid face. It's applicable to planar and curved structures. It can consider different loading scenarios. 2 partial double-layer grid shells are designed based on the optimization results, and the analysis shows their uniform deformation under the external load. Future work includes detailed investigation of the mechanical properties of the partial double-layer grid shells, incorporation of user-defined geometries, consideration of buckling and displacement in the optimization problem. Thanks for your attention. I'm happy to answer your questions.